Alright, so, yeah, hello everybody, thank you for clicking on this video, and, this is going to be an interesting video. It's just going to be disjoint from any sort of, other series that I have going on in my channel or whatever. It's just a standout video, where I'm going to be talking about, a really cool connection between the Riemann hypothesis and topology. Now, I've actually done the exact same video. It's an unlisted video on a whiteboard, but I felt that it was long-winded, and I just wanted to make this video as concise, and also the handwriting or typing or handwriting, whatever, as clear as possible. So I'm going to just see how it looks with slides. Now, I am in a different place. I'm pretty much in Scotland, although I'm kind of on the border between Scotland and England. But anyway, I forgot to bring my actual digital pen thingy with me, so I'm not going to be making as many annotations. I'm just going to be using my mouse to maybe underline stuff or whatever. But yeah, so without any more waffling, let's just get straight into the video. So the plan for this video is to kind of introduce the Riemann hypothesis. Okay, that's a famous problem in mathematics, and then a kind of a simplicial complex. So this is a piece of jargon which basically I'm just going to be using, not because you need to know what it is, just because it's the most convenient thing for me to be saying. You don't really need to know the precise definition of an abstract simplicial complex. That's just, the thing, just what happens to be the name of the thing we're going to be dealing with. And then this right here, that will become more clear what this means as we go forward. And then at the end, I'm going to basically just go and kind of just reinforce the point of all of this work we've done here. And, so we're going to give a couple of consequences, and then at the end, of course, I'm going to just say, we're just going to quickly recap what the hell we've actually done in the 22 slides that I've prepared. So, okay. So, firstly, let me introduce the Riemann hypothesis and the zeta function. So, when the real part, so it's defined on complex numbers, and when the real part of S is bigger than 1, we define zeta of S as this sum here. Now, this is quite a natural thing to study. Of course, you have the, what's it called? The harmonic, no. You have the, oh god, I've forgotten what it's called, but you also have the Basel problem. You have stuff like this. Sums of this form are quite interesting, so, why not just generalize it into a single function? Now, the interesting thing about the zeta function is that you can analytically continue it, so you can make it make sense for all complex numbers, except for 1, but okay. Now, this is the precise kind of analytic continuation, so you can use this to define the zeta function on all of the complex numbers, not just when the real part of S is bigger than 1. And what you'll see is that there are trivial zeros. Now, this is when this sign factor becomes 0, then the whole thing becomes 0. And this happens at negative even integers. And the reason it doesn't happen at positive even integers is because this will be 0, yes, but then this will diverge, so those two factors will cancel out at positive even integers. So, the zeta function has trivial zeros is what they're called, when you input a negative even integer. But the Riemann hypothesis is asking us about where are the other zeros. And what Riemann noticed is that they all seem to be of the form 1/2 plus it. And so, of course, the Riemann hypothesis asserts that the non-trivial zeros of the zeta function are all of the form 1/2 plus it. And now, this is a really big problem. It has, deep connections to a lot of stuff. But in this video, we're going to be talking about how it's connected to topology. or how it can be, more precisely, how it can be restated with topology is what we're going to be looking at. And of course, this is a really big problem in mathematics, and there have been a bunch of different approaches. None of them have worked so far, but in this one I'm just going to be looking at not an approach per se, but just a really interesting way to equivalently restate this statement here. So, to do with this is the Mertens function. Now, the Mertens function is a number theoretic function, and it's defined as the sum from k equals 1 to n of these Mobius functions. Now, the importance of this function doesn't really lie in the exact value that you get. It actually lies in the growth of this function. And when I say importance, I really do mean that the growth of this function is important, because the growth of this function relates to both the prime number theorem and the Riemann hypothesis. So the prime number theorem is true if and only if the absolute value of this m of n is less than epsilon times n for all epsilon greater than 0 and for n sufficiently large. And the Riemann hypothesis is equivalent to saying that the absolute value of this function is less than n to the half plus epsilon for all epsilon bigger than 0 and for n sufficiently large. Now, an interesting note about this one here is that there was some stronger conjecture about the Mertens function being bounded by the square root of n, but that was disproved by, I believe, Hardy or someone like that. So, but of course, this statement here hasn't been disproved. That would be huge. But okay, maybe not the most incredible thing, but the thing that we're going to be looking at in this video is the fact that up to a sign, the Mertens function is literally just the Euler characteristic of a certain simplicial complex, which I'm going to be introducing, and all of this jargon here will be explained in due course. So yeah, let's go on and define this simplicial complex, which I've been building up to. So let's just recall the definition of the Mobius function. So the Mobius function is defined as this. So it's defined as -1 to the cardinality of the set of prime factors of n, if n is square free, so that is not divisible by a perfect square, and it's 0 if n isn't square free. So that's our definition of the Mobius function. Now the Euler characteristic of a simplicial complex is this sum over the number of n simplices, and it's an alternating sum. Now, okay, again, you don't need to know what that means. This just kind of, I just keep this kind of form here in mind. Now, our goal is literally to construct, kind of artificially construct a simplicial complex, and we want this sum to be of the form, of exactly the form of a sum of Mobius functions. Again, I'm with a mouse, so I can't write at all, but you know what I mean. Because this is this is going to give us, like, an alternating sum when we sum all of these guys, and this is obviously an alternating sum, so we just need to kind of, artificially construct such a function. I mean, such a abstract simplicial complex. So the trick is to define our simplex as this. So it's the set of all, and remember, P of k means set of prime factors. So it's a set of all of these prime factors such that k is square free and k is less than or equal to n. And this actually gives us the abstract simplicial complex that we desire. So our Mertens function is again, we set up to a sign, so it's negative, because it doesn't really matter about the sign, because remember that all of the important stuff happens when you just take the absolute value, and the absolute value of this is equal to the absolute value of that. So okay, the sign doesn't really matter that much. of course it doesn't matter, but like, I mean, the fact that it's negative, that doesn't matter that much. And actually we have to subtract 1, so we're just denoting by C, the Euler characteristic minus 1. Now, we've done that, and the rest of the time what we're going to be talking is basically the consequences of this. So, of course, this is a nice fact, but it doesn't really do much unless we can kind of study this Euler characteristic. Now, the great thing about this is that the Euler characteristic is a topological thing, but so we study it using topological methods. But in this case, because our Euler characteristic turns out to be such an important function in number theory, we're kind of using topological methods to study a number theoretic thing. And so that's what the importance of this lies. So we can't really talk about Euler characteristics without talking about Betti numbers, especially when we're talking about more abstract shapes. I mean, not shapes, abstract objects like simpler circle functions. So Betti numbers are literally just a way of rewriting Euler characteristics as a different sum. So in this case, the Euler characteristic is equal to this sum right here, from k equals 0 to infinity, and it's just an alternating sum of these Betti numbers. Now, the precise definition and the normal definition is that the kth Betti number is the rank of the kth homology group of X. Again, no need to know what the jargon is, this is just a precise definition. And the great thing about these Betti numbers is that they admit a much more simple form, which when we're dealing with this delta n, this complex which we defined above. And so, of course, because this right here denotes the Euler characteristic minus 1, we have to define our Betti numbers in this case as the rank of the reduced simplicial homology. Anyway, so that's just this little bit of technical jargon here, basically. All of this just technical stuff about what precisely it means, but this is really the importance of the Betti numbers, at least for us, is this fact here. Actually, scratch that. The importance for us lies in this fact here. And it's literally because of this right here, because of this formula here, and of course because the Mertens function is that Euler characteristic. So we've defined the Mertens function as this sum of Betti numbers. Right now these Betti numbers are still probably quite mysterious to you because they have such a technical definition, but the beauty of this right here is that they admit such a very nice form when we're dealing with the Betti numbers of this delta n thing. So we have to do some setup, unfortunately. It's quite a long thing to do, but it's worth it. So, let's just go straight into it. So for any real number x bigger than 0, we define sigma of x to be the number of square free integers in this interval. Sigma odd x is obviously odd square free integers in that interval. Sigma k of x is square free integers in this interval of weight k. And then, of course, sigma k odd is odd square free integers in that interval of weight k. And the weight of a number is just the number of prime factors. So, for example, a number which has weight 1 would just be a prime number. That's, for example. And of course, sigma even and sigma even k are, of course, defined in the exact same way, except replacing odd with even. Okay. Now, a couple of side notes, not that important, but just side notes about this function are that a classic approximation by Landau, I think is how you pronounce that name, is that this sigma k is asymptotic to this thing. But the really cool thing is that when k equals 1, obviously this part is going to go away, and numbers of weight k, of weight 1 are obviously just prime numbers. So our sigma 1 is literally just our prime counting function. Of course, again, I don't have my pen, so I'm trying not to write as much, but our sigma 1 is just the prime counting function. So this approximation when k equals 1 is literally just the prime number theorem. So that's cool. And multiplication by 2 will give us a bijection. As you can see there, that's just another slightly interesting fact. The reason for that is multiplication by 2. Well, of course, it will make the odd numbers even. X over 2 will correspond to x, and multiplying by 2 adds 1 to the weight. So, because of course, if you multiply this thing by 2 here, then that's a prime factor, so you're just going to add 1. So, okay, there you go. So that's why that is true. But the reason that we're setting all of this stuff up is not random. It's because the kth Betti number of delta n is precisely, these sigma odd function thingies. It's just, you combine a couple of them in this way, and you get a form for the beta k's, which should be much more understandable than the rank of reduced simplicial homology. So, that's nice, but we're not going to settle for this. We're going to try and make this nicer. And in fact, you can. The way that we're going to make this nicer is, well, we don't like this odd right here. We're just going to get rid of this odd stuff. So, that's exactly what we're going to do. The theorem is that sigma k odd is this alternating sum of sigmas, and sigma odd is this, sigma k odd is this alternating sum of sigma k minus 1, blah blah blah, and sigma odd is this alternating sum of just sigmas. And the proof is really easy. Because of this bijection here, which I stated earlier, okay, so sigma k is obviously going to be sigma k odd plus sigma k even. Again, I don't have my pen on me, so my handwriting is going to be awful, but the sigma k of x is going to be equal to sigma k odd plus sigma k even, so we can decompose it in that way. But because sigma k even is equal to this thing, we have sigma k odd x plus sigma k even x is equal to sigma k odd x plus sigma k minus 1 odd of x over 2. Rearrange that, of course, and we get this. We get this thing right here. Now, what is good about this is that this is a form for sigma k odd. So, of course, it's obviously also a form for sigma k minus 1 odd. So this right here is equal to itself, it's equal to sigma k minus 1 of x over 2 minus, and then we're going to get sigma k minus 2 odd of x over 4. So it's basically this is a recursive definition, if you see what I mean. And then, of course, you can plug it in again for sigma k minus 2 odd of x over 4, and so on, and you'll get the first result. The second one is just obtained by summing over all of the k's. So that's easy too. So, we got a form for the Betti numbers in terms of these number theoretic functions, and then we got rid of this slightly ugly odd part of them. So, now that we've done that, we're going to study the asymptotic behaviour of these Betti numbers. Now, of course, the end goal is to study the growth of the Mertens function. So, of course, studying the asymptotic behaviour of the things that define the Merton function, of the parts of the sum that define the Merton function, is obviously logical. And so there's a three-part theorem which I'm going to state, all different aspects of the growth of the asymptotic behavior of the Betti numbers, but these two here require a lot of computations, which I don't really want to get into that much. So this one is much nicer. This is a much nicer thing to prove. So we're just going to go ahead and prove this number one thing here. So what it says is that as n tends towards infinity, we have that the sum over all of the even numbers of Betti of these, so all of the even Betti numbers of delta n is asymptotic to n over pi squared, and so is the sum over all of the odd Betti numbers. It's also asymptotic to n over pi squared. So, if we let a of n equal to this thing, and b of n equal to this thing, then we get the following. So, part 3 of this theorem says that when we add both of these things together and then divide it by n, we're going to get 2 over pi squared, because, we're just going to cancel out the n, and that's 2 over pi squared. As n goes to infinity, of course. And the prime number theorem, as we've established before, as we established at the very start of the video, states that when you subtract these two sums, again, you're going to get an alternating sum, so you're going to get the Merton's function of n over n. But as we've established with the prime number theorem asserts that this is going to go to 0 as n goes to infinity. And therefore, when you add this and this, you get 2a of n over n, and this is still going to go to 2 over pi squared, because adding 0 to this is going to go to 2 over pi squared. And then, just rearrange, multiply by n over 2, and you're going to get that a of n tends towards n over pi squared as n goes to infinity. And again, you can use the exact same reasoning for b of n. So that's, just a taste of how you would study the asymptotic growth. And that's quite a neat argument, I'd say. So, and don't forget that this is indirectly studying the growth of the Merton function, which is really important, of course. And finally, what we're going to do, so we've studied some of the asymptotic behavior of beta of these Betti numbers. So I gave a three-part theorem, all of which studies different aspects. What happens if you sum the even ones? What happens if you sum all of them? What happens if you just, you just leave it? And so now, what I'm going to finish up with is some concrete number theoretic consequences to really convince you that what we've done is useful. And then, again, reinforcing the idea that what we've done is useful, I'm going to, again, at the end, recap what we've done. So, again, as I said, this is just a quick addendum, and this is just some purely number theoretic results which you can derive using facts about the Betti numbers of this complex. So, precisely the fact that they're completely determined by those functions which we defined above, which count, square free integers in certain intervals, can help us to find certain bounds. And more precisely, these bounds are the following. Knowing the number of odd square free integers of weight k plus 1 in a certain interval, one can actually obtain a lower bound for the number of such integers of weight k in a smaller interval. And all we need is a couple of extra definitions. So, this right here is basically, sigma k plus 1 of n. And knowing this thing right here, you can obtain a bound for sigma k of n over 2. So, okay. So that's quite a nice result. All we need is the following definition, and it's more complicated than it looks. So actually, for any k and n bigger than 1, any integer n can be uniquely expressed as this slightly combinatorial, I would say, sum. Then what we do is we define the following two functions as follows. So as slightly shifted, we could say, shifted versions of these sums. So for this one, you shift the bottom part of this binomial coefficient, and for the top one, you shift both the top and the bottom. And then what you do is you obtain lower bounds for these sigma k odds given this thing right here. So more precisely, this first one is about when you just shift the bottom and of this sigma odd, and this is less than or equal to sigma odd k of n over 2. And the second one is when you shift both the top and the bottom parts of the binomial coefficient of the unique number, the unique expansion that represents whatever this number is. When you shift both the top and the bottom, you get a number which is definitely less than or equal to sigma odd 2k of n over 2 plus sigma odd 2k minus 1 of n over 2. And so that's a purely number theoretic result, which you get from a slightly messy argument using Betti numbers and basically stuff we've studied in this video. And that's a purely number theoretic result, and we got that using pretty much purely topological methods. All of the blanks that I've left out are, ugly computations or really technical topological jargon, which I didn't really want to include. But hopefully you get the sense of what's going on and the type of arguments which we're using. So finally, what have we done? Well, firstly, we restated the Riemann hypothesis as a problem concerning the Euler characteristic of a slightly artificial abstract simplicial complex. So that's the first thing we did. If you'll recall at the very start, we realized that the growth of the Mertens function is really important. We constructed an Euler characteristic which is precisely the Mertens function, and bam, Riemann hypothesis restated as a topological problem. Then we studied the asymptotic behavior of these Betti numbers, and that was important because, of course, our Mertens function is literally an alternating series of those Betti numbers. And then we managed to get some nice bounds for the number of odd square free integers of weight k, blah blah blah. And that's a purely number theoretic result, and the best part is we used it using pretty much topological methods. So hopefully you can see, it's definitely not a thing which is common. Oh god, I did not mean to do that. It's definitely not a thing which is common to see how number theory and topology come together to work together and get nice results. But I find it quite nice that, this thing exists, right? That, this weird complex which, seems totally random to study, and one of the biggest problems in number theory can come together so nicely and can be, as mathematics often, as is the nature of mathematics, they're somehow interconnected. And so thank you for watching. Hopefully this is something you didn't know. Hopefully it's something that you found quite interesting. And I will be having a blog post in the description where I post the slides. And I'm going to be writing about two other slightly smaller connections between topology and number theory. Namely, I'm going to be computing a weird sum using cohomology, and I'm going to be showing the infinitude of primes using a special topology on the integers. So that's everything I want to do. Thank you guys for watching, and have a good day. Goodbye.